Hey guys, so in the last video we talked about the tensor product, where if we have some state, let's say capital psi, which is a product, a tensor product of psi and ket phi, then this is necessarily a linear combination of the following states. So let's say this is a combination A, ket 0 plus B, ket 1. And this is a linear combination C, ket 0 plus D, ket 1. Then this state, which is the tensor product, is going to be AC, ket 0, 0, plus AD, ket 0, 1, plus BC, ket 1, 0, plus BD, ket 1, 1. So we know that that this combined state, the product state, is a linear combination of all of these. However, what if we have a state like this, where our product, as it were, is a linear combination like this, ket 1, 1. Now, if we think about it, the coefficient of ket 0, 1 and ket 1, 0 are both 0 in this state. That means either if both of these are 0, then one of these terms has to be 0, and then that would make these terms 0, which can't happen. So the key idea of this state is you cannot break it down into a tensor product of one state tensor multiplied by one state. Mathematically, we call this an entangled product. Now, this is a basic example of an entangled product, where if we measure one qubit as 0, then the second qubit is necessarily 0. And if we measure one qubit as 1, then the next qubit is necessarily 1. And we have a 50% probability of doing either one of those. Now there's 4 types of basic entangled states, where if we measure one qubit as one state, then the other is necessarily that state. And for the rest of this video, I'm just going to write these states down. These are called Bell states. And they're the 4 basis states of this 4D system of 2 qubits, because they are linearly independent of each other. So this can be represented as psi plus, that's equal to 1/2 ket 0, 0, or ket 0, 0, plus 1 over, not 1/2, 1 over root 2 ket 1, 1, which is what we just wrote. There's psi minus, then there's phi plus, and phi minus. These are just standard notations. So each one of these is going to be 1 over root 2 ket 0, 0, minus 1 over root 2 ket 1, 1. And this is going to be 1 over root 2 ket 0, 1, plus 1 over root 2 ket 1, 0. And this is going to be 1 over root 2 ket 0, 1, ket 0, 1, minus 1 over root 2 ket 1, 0. And these 4 Bell states all follow the property of the first Bell state we talked about, which is that they cannot be represented as a tensor product of 2 independent qubits. Basically, if we measure one qubit is entangled with the other. If we measure one, the state of the other qubit is automatically determined. That's the basic idea of entangled products and entangled states.